So in algebraic geometry, we have this obsession, really, with classifying things. I mean, imagine you could create a master catalog of every possible geometric shape of a certain kind. Well, that catalog, which turns out to be a geometric space in its own right, is what we call a moduli space. And for a long time, mathematicians kind of just used them, assuming they were there. But, as we're going to dive into today, thanks to a really fantastic article by Jared Alber, the real question is way, way deeper.
Right, so here's the absolute heart of the matter. Why should these beautiful organizing catalogs exist as something we can actually get our hands on? I mean, why should they be concrete algebraic varieties? Things you can actually define with polynomial equations. It sounds simple, but this question has driven more than 150 years of mathematical innovation. It literally forced geometers to invent entirely new ways of thinking about what a space even is.
And you've got to understand, this isn't a story with just one hero. It's more like a multi-generational epic. It all kicks off with Riemann's incredible intuition back in the 1850s. Then, fast forward about a century and the torch gets passed to the one and only Grothendieck, who just completely rewrites the rulebook in the 60s. After him, Mumford comes along in the 70s and builds this powerful machinery, geometric invariant theory, to actually construct these things. And all of that leads us right up to today, to the modern, incredibly powerful language of algebraic stacks.
Okay, so here's the plan. We're going to start with Riemann's original problem. Then we'll see how the search for a proper language hit a major roadblock. From there, we'll look at the two brilliant paths that were forged to get around that problem, which, by the way, revealed a whole new kind of geometry. And finally, we'll take a quick look at where all this is heading today.
All right, Section 1, Riemann's fundamental problem. So our story really begins with the legend himself, Bernhard Riemann. He's writing this incredible paper back in 1857, and he's looking at a whole class of shapes, and asks a question that sounds deceptively simple. How many numbers does it take to pin down one of these shapes?
And he called these numbers the moduli. And get this, he even nails the answer 3g minus 3. But, and this is a huge but, he had the right count, but the mathematical tools to actually build the space that these numbers were supposed to live in, they just didn't exist yet. The man was working light years ahead of his time.
Okay, now we jump forward, from functors to stacks. Because for almost 100 years, Riemann's idea was just that, a brilliant intuition. To make it solid, to make it rigorous, math itself needed a revolution. And the person who led that charge, who totally shifted our perspective, was Alexander Grothendieck.
So Grothendieck comes along with this totally radical idea. He says, look, stop thinking about a space as just a bunch of points. Instead, a space is defined by its relationships, by how it maps to all the other spaces. It's kind of like a probe, right? To really understand something, you have to see what it looks like from every single possible angle. And this probing is what we call a functor. In our case, the functor is a rule that says, give me any test space, let's call it T, and I'll give you back all the families of curves you can build over T.
And this right here, this is the dream scenario. This is what we want. The idea is that any path you draw in your moduli space, that's the thing on the left, should correspond perfectly one-to-one with a smoothly changing family of curves on the right. If you can get this perfect match, then we say your moduli problem is representable by that space. It's clean, it's beautiful, it's perfect.
But, of course, this beautiful dream has a villain. And the villain's name is automorphisms. What are those? Well, they're the hidden symmetries of the objects themselves. Think rotations, reflections, that kind of thing. And as you're about to see, if one of your objects has even a single non-trivial symmetry, it just throws a giant wrench into the entire machine. Okay, so check this out. This is exactly where everything falls apart. Imagine a really simple, boring family of curves. It's just the same curve C copied over and over again along a line. Now, let's say that curve has a symmetry, like you can rotate it 180 degrees and it looks the same. Well, you can use that symmetry to glue the ends of your line together, but with a twist. All of a sudden, you've created a non-trivial family out of a trivial one. Every curve in the family is still identical, but the family itself is twisted like a Mobius strip. And that's a flat-out contradiction. You've got a loop in your parameter space that should be trivial, but isn't. And that one problem, it's a showstopper. It proves that a simple, well-behaved moduli space just can't exist.
So what do? This automorphism problem was basically a fork in the road for mathematicians. It forced them down two totally different paths. One path was extrinsic. It tried to find a clever way to work around the problem. The other was intrinsic. It tried to embrace the problem.
All right, path number 1 was forged by David Mumford.
It's called geometric invariant theory, or JIT for short. And the strategy is just brilliantly pragmatic. The idea is, okay, first, let's just dump all of our curves into some huge, well-understood space, like projective space. Then, we figure out how the symmetries act on everything. And then, we just build our moduli space by taking a quotient. The real magic, the genius of it all, is figuring out which points are semi-stable. Basically, which are the good curves that won't mess everything up when you take that quotient.
But this whole approach, this extrinsic path, it sparked a really fascinating debate between the giants of the field. Grothendieck, in a letter to Mumford back in '62, basically said, "I'm afraid you won't convince me." He felt it was an unnatural method because it depended on choices you had to make from the outside, like how you embed your curves in projective space. He was searching for a solution that was pure, something that was totally intrinsic to the problem itself.
So to get GIT to actually work, they needed a key idea, the stable curve. And you have to understand, this definition is basically purpose-built to fix the automorphism problem. Stability is a condition that's designed to kill off the most troublesome symmetries by allowing only very simple nodal singularities. And this is the key part, demanding that the automorphism group is finite. You're pretty much just filtering out all the bad apples, the curves that were breaking the machine.
And here you can see exactly what that means in practice. The curve on the left, that one's stable. It's well-behaved. The one on the right, though, is unstable. Why? Because one of its little components has an infinite automorphism group. You can kind of see you can scale it. And that makes it totally impossible to deal with using GIT. So stable is what gives us the right collection of objects to build our catalog with.
And that brings us to path number 2, the intrinsic solution that Grothendieck was looking for all along, the revelation of stacks. This is a total game changer, because instead of trying to get rid of automorphisms, this new language finds a way to build them directly into the geometry of the moduli object itself.
Which leads us to the geometry of stacks, and this is so important to grasp. Stacks aren't just some technical patch for a broken definition. No way. They are a fundamentally new type of geometric object, one that has symmetry baked right into its very core.
Okay, this table right here, it's basically the Rosetta Stone of modern moduli theory. It lays it all out. What it's telling us is that the kind of automorphism group you're dealing with dictates exactly how stacky your moduli problem is. If you have no automorphisms at all, great, you get a classic scheme or algebraic space. If you have finite automorphisms, then you get what's called a Deligne-Mumford stack. That's our moduli space of stable curves, MG. And if you have more complicated reductive groups, well, then you need a full-blown algebraic stack, like the space of vector bundles.
And this image gives you such a great feel for what a stack is actually like, geometrically. It's not just a smooth surface. It's more like an orbifold. It's mostly smooth, but it has these special creases or singular points. And what are those creases? Well, they are precisely the spots where the objects you're classifying have extra symmetry. The geometry of the stack itself is a map of the symmetry data. Every single point remembers the symmetries of the object it represents.
So with this new language in hand, we now have this incredibly powerful and completely intrinsic 6-step recipe for building these things. You start by showing your problem actually forms an algebraic stack. Then you tick off a series of crucial properties. You show it's bounded, it has semi-stable reduction, and so on. And if you can do all that, it guarantees that a nice moduli space exists as a good quotient. And the best part? You never once had to pick some arbitrary embedding into projective space. It's all internal.
All right, so after this amazing century-and-a-half-long journey, where are we now, and what's next on the horizon?
So what we've seen is how this one question, why do moduli spaces exist, went from being a nagging foundational puzzle to being the main engine for creating an entirely new language for geometry, and stacks give us the answer. They teach us to treat symmetry not as a bug to be fixed, but as a feature to be celebrated and encoded.
And believe me, the story is far from over. This whole framework is the engine driving so much of modern research. It's what powers the construction of moduli spaces in Gromov-Witten theory, in the minimal model program with K polystable varieties, and in the incredibly deep world of Bridgeland stability conditions. It's everywhere.
Which kind of leaves us with one last big question to ponder. Every huge leap forward in our understanding, from manifolds to schemes to stacks, it acquired the invention of a whole new language. So, what's the fundamental problem that we're grappling with right now that's just waiting for its own revolutionary new language to come along and crack it wide open?